Hello everyone. This is my presentation of my project OFDM simulation using Matlab for wireless communication course. I've divided my presentation into 5 parts, which is introduction, description, evaluation, related work, summary, and conclusion. OFDM is a frequency division multiplexing scheme used as a digital multi-carrier modulation method. A large number of closely spaced orthogonal subcarrier signals are used to carry data on several parallel data streams or channels. It is widely used in modern communications systems such as digital television and audio broadcasting. DSL Internet Access, Wireless Network, Powerline Network, 4G mobile communications. It has its advantages and disadvantages. For advantages, it has high spectral efficiency when compared with other spread spectrum methods. It is robust to narrowband cold channel interference and to ISI. It is slow implementation. It has slow implementation costs due to IFFT efficiency. For its disadvantages, it has loss in efficiency due to guard interval. It has peak to average power ratio, which is PAPR, and it is sensitive to frequency synchronization and Doppler shift. Compared to other systems such as GSM system, which has a bandwidth of 200 kHz. OFDM can have as much as 20 MHz. Therefore, its data rate is higher. Assume the bandwidth of an OFDM system is 10 MHz, so its single time t equals 0.1 microsecond, and assume the delay spread of this channel is 2 to 3 microsecond. When delay spread is far more than symbol time, it leads to a problem, which can be degradation, loss of performance of the wireless communication system. That problem is called ISI, that is inter-symbol interference. As bandwidth B increases, symbol time 1 divided B decreases, which poses a significant challenge in a broadband wireless system. So in order to overcome this problem, what OFDM do is that it places a subcarrier in each subband. Assume it has n subbands, so the bandwidth in each subband is b divided n. For instance, if the bandwidth is 10 megahertz, n equals 100, then bandwidth of each subband is 10 kilohertz. Symbol time in each subband equals n divided b. In this case, t equals 100 microseconds, so that t is far larger than td. Therefore, there's no ISI in new system with multiple subbands and subcarriers in each band. Such a system with multiple subbands and subcarriers is termed as a multiple carrier modulated system, MCM, which is precursor of OFDM. This figure demonstrates the process of the modulation and demodulation, which is performed using an FFT and IFFT pair. The transmission of n symbols begins with interpreting each symbol to be transmitted as a complex number that collectively define an n-symbol set of complex valued symbols. The complex array is presented to an n-point IFFT, which converts the symbol array into an n-symbol complex time series. The complex time series is transmitted and coded by an FFT located at the receiver, which converts the complex time series back into an array of n complex symbols. For this project, I developed a 64 channel, 64-point IFFT FFT QPSK, which is showing in this figure. And I used Matlab studies to test my proposed solution. Using Matlab's additive white Gaussian noise, I created a 2 to the power of 6 multiplied 2 to the power of 6 metric of noise added random QPSK symbols. From the 2 to the power 6 multiplied 2 to the power 6 symbol matrix, 2 to the power 6 symbols at a time, we can get the data, which is then processed by a 64-point IFFT and FFT in a channel that contains additive noise aligned with OFDM solution shown in figure 3. Then I analyze SER, that is the symbol error rate. This is figure 3 that it shows SNR cases for the OFDM system. Remember that noise is complex. Assume that all signals are transmitted across a lossless, flat, delayless channel. A possible outcome is shown below. When we return the value of SNR to 25 dB, the outcome is showing as this. And for SNR equals 15 dB, the outcome is this. For SNR equals 5 dB, the outcome is this. So compared to these three charts, three diagrams, that we can infer that the higher the SNR is, the clearer the signals is after transmission. And I also compute the symbol error rate SER on SNR equals 25 dB, 15 dB, and SNR equals 5 dB. So we can conclude from this chart that if SNR is higher, then SER becomes lower, and if SNR becomes 25, then SER becomes 0. The higher the SNR is, the rate of decreasing of SER is. Related work. Primary related work deals with a variety of methods of channel estimation, including block type pilot and combo type pilot. For COM type pilot, part of the subcarriers are always reserved as pilot for each symbol. And for block type channel estimation, OFDM symbols are transmitted periodically as shown below, and all subcarriers are used in a specific period as pilot. Summary and conclusion. The basic principle behind multi-carrier modulation is to replace a wideband signal with many narrowband signals which are transmitted at the same time and places a subcarrier in each subband. The larger SNR is, the clearer the signal is after transmission. And the third one is that by simply taking the values of SNR, we are able to observe the SER variation. SER decreases as SNR increases. This is my code for this project. As you can see, for this part of code that I I create binary data for 64 2-bit symbols. I changed the S and R to from 5 dB to 15 dB to 25 dB. And I use the QPSK modulator system. And for the bottom 3 lines, I use the IFFT transformation and FFT transformation, and I add noise into it. For this part of code, I use this code to compute the variation of SCR in change of the values of S and R.